Hello James, welcome back to another video. This is the ultimate grind for BITSAT 2025. This is the question bank series wherein we are getting 10 questions stronger in every chapter for BITSAT 2025. Today we are discussing the chapter of electrostatic potential and capacitance. So previously we have discussed all the chapters of 11th standard in this series. So if you have missed out it, I'll link it in the description of this video. You can go watch it once you finish with this one. Okay. So you know the drill. Firstly, we discuss about the previous year trends, which questions are being favored for BITSAT across the previous years from the particular chapter, and then we dive into the questions, right? So let's see the trends. So from potential, electrostatic potential, KQ by R, okay, from there 7 questions. Then we have conversion from electric field to potential, 3 questions from there. Capacitance, 18 questions, okay, so that is an important topic. And in that also, if you want to see the subdivision, so you have grouping of capacitors, so series parallel, 7 questions, dielectric, 4 questions. Then we have energy of the capacitor or the force on the plates, we have 3 questions from there. Charging, discharging, 2 questions, and in general 2 questions about capacitors. Okay, so that's the brief breakup over the previous years. Let's hop into the questions and let's get stronger with every question we answer. 1 and 2 over here. In question 1 we have a point charge small q which is rotating around a charge capital Q. Okay, you are supposed to tell it is rotating in a circle of radius r. You are supposed to tell what is the work done during this process. Okay, you can easily see that the displacement is like this. Okay, the force will be either repulsive, suppose they are of the same parity, okay, plus plus or minus minus. So here the force will be this direction, right, outward, pushing it out, and the displacement is along this, right, tangential direction, so d. So you can see the angle between f and d, f is perpendicular to d, right. So here the work done will be 0 because work is fd cos theta, right, cos 90 is 0, so this will be 0. Or you could see it some other way, so 0 is the correct choice over here. You could also use dimensional analysis over here, qq by r, qq by r, that is work. But if you see the dimensions of this and this quantity are not work, right, so you can eliminate these two options. But also the other way to do is q into delta v. Okay, this is the work done. And since if you see, you can take it from here to here, any point on the circle, it's a point on the equipotential surface, right, for this particular charge q. The potential at this radius r is kq by r, okay, at this point or at this point or this point or this point. Okay, so basically the charge is moving on an equipotential surface. Potential is same throughout, so delta v is 0, right, no change in potential, whether it is here, here, anywhere on the surface, okay, where it is moving. So delta v is 0, meaning work is 0. Okay, so that is the actual concept of to do this question. Okay, this is how it's moving, so you can use the basic definition of work as well. So let's come to question 2. Here we have a dipole which is initially lying along the field, so suppose minus q to plus q, so this is your dipole moment. Of course it goes from minus q to plus q, right. So then we have the electric field which is also in the same direction, so the dipole is along this, right, so both are in the same direction initially. The work done in rotating the dipole by 90 degrees. So initial configuration is this dipole, so minus q plus q, and we have the dipole moment minus to plus. So then we are rotating it. Okay, so minus q plus q, and field is like this. Okay, so what is the potential energy? You might directly know the formula for this, that P cos theta initial minus final, right. So or you could look for the change in the potential energy, right, since electrostatic force is conservative, change in the potential energy will give you the work done. Okay, so what is the initial potential energy? The potential energy in case of dipole, by the way, is given by P cos theta minus. Okay, so initially if you see it is minus PE, right, and cos 0, both are in the same direction, theta is 0. So this is initial potential energy. What is the final potential energy? P cos theta. So this is 90 degrees, right? So the dipole moment is negative to positive and electric field is like this. So 90 degrees angle between them. So cos 90 is 0. So finally it is 0. So work done will be nothing but final minus initial potential, right? Change in the potential energy is work done for a conservative force. So it's basically PE, which is option D. Okay, so that's about these two questions. Over to the next one. Coming to question 3 and 4. In question 3, we have a parallel plate capacitor which is charged to a potential of V. So C is charged to a potential V by means of a battery. Okay, this is small diagram. So this is how it is done. So the distance between the plate is increased. So first you'll disconnect the battery. Okay, so it is now an isolated capacitor, which is important because the charge on this capacitor will remain constant, right? If you keep the battery connected, the voltage will remain constant, right? When you separate it out and you treat it as an isolated system, charge on an isolated system is constant, right? Conservation of charge. So here the charge is going to remain constant. You are supposed to tell if the distance between the plates of the capacitor is increased. So D we are increasing, what will happen to the voltage, okay? So if you see the equation, C is equal to Q by V, right? We know that uh, Q is going to remain as constant, Q is our constant. So you can relate C and V, right? So C is inversely proportional to V. Q is constant because it is a isolated system. So charge is inversely proportional to the voltage. Sorry, not charge. Capacitance is inversely proportional to voltage. So what is happening over here? We are increasing the separation, plate separation. So plate separation, capacitance is given as A epsilon naught by D. This D is the plate separation, right? So we are increasing this D. So we are increasing D, meaning we are decreasing C. So if we increase the denominator, the C will decrease, right? So C is decreasing, but C and V are inversely proportional. So V will increase. Okay. So once again, C and Q are, Q is constant, C is inversely proportional to V. So this is what we obtained. And we saw that we are increasing D. So if we are increasing D, we are decreasing C. If we are decreasing C, inverse relation, so increasing V. So V increases. Okay, so the potential will increase. Now let's come to this one. Here we have three uncharged capacitors C1, C2, C3 connected in this fashion. Okay, the potential at A, B and D is given. It is V1, V2 and V3 respectively. So you are supposed to tell what is the potential at point O. Okay, so some of you might directly know this potential at a common point, right? So pat on your back and move on to the next question. And also you can see dimensional analysis at play over here. Okay, you can do dimensional analysis and see which one will have the dimensions of voltage, right? If you see, it's not difficult to see. This won't have, this won't have. This is V by C, right? Basically V by this is V square by C square, again not voltage, right? Again this is V cube by C cube, again not voltage. Only this option has correct dimensions of voltage, right? So it is CV, CV, so CV by C. So CC cancels and you have voltage. Okay, so you can do dimensional analysis as well. So we will have to use KVL. So C1 and we'll have the charge. Okay, so actually KCL. Okay, so current law, right? Because we'll balance the current. So this current, suppose it's splitting in these two branches. So that is what we are doing. So basically, if you see current in a capacitor will be C dV by dt, right? Because if you have Q, Q is equal to CV. So your current, which is the rate of change of charge, is C dV by dt. C is constant, right? So C dV by dt. Okay. So that is what we are applying. So dV by dt. Dt is anyways, if we bring it to one side, it will be 0, right? So so dt can be taken to the other side and it is basically 0. So we'll just see the differences in voltage. So C1 difference in voltage, C2 difference in voltage, C3 difference in voltage. Okay. Now this common point is treated as the hero, so it will appear everywhere. So this will be V1 minus V0. Okay, and this are brought to the other side. So on one side, again you'll have minus V0, so V2 minus V0 and V3 minus V0. Okay, so it is the hero. So V2 is over here, right? So and V3 is over here. So C into the delta P. Okay, delta T is taken to the other side. It's basically 0. Okay, now what will be this? So what do we have? So again you'll see C1 V1 plus C2 V2 plus C3 V3, right, and this is common, right, minus V0 is common, minus V0, and you'll have C1 plus C2 plus C3, right, from the second term of each of the brackets. So you can see V0 will be nothing but C1 V1 plus C2 V2 this side plus C3 V3 upon this C1 plus C2 plus C3. Yes. So that is your option A. Although we found it from dimensional analysis, this is the correct concept to do this. So over to the next question. So let's come to question 5. Here we have a capacitor. You might have done this type of questions wherein you have dielectric within the capacitor. So here it's also given in the question that this is a series connection. So you might not be given about the connection type. So you can make it out since this is in one line. It is a series connection. So you have K1 and K2. We can split it this way. We can observe it this way. So this one has thickness D1 and this one has thickness D2. Okay. So this can be thought of as a dielectric slab. So effectively this is a dielectric slab with basically the thickness D1 plus D2, right, and some K effective. Okay, you are supposed to find this effective dielectric constant. Okay, so basically you will find the C equivalent for this combination, and in this C equivalent you'll have the K effective, right. So that will give you the value of your K effective. So C equivalent, so this is a series combination as I told you. So C equivalent will be product upon sum, right, or the sum of their reciprocals. So for 2 it is basically C1 C2 upon C1 plus C2. So C equivalent will be basically, if you see C1, what is C1? A epsilon naught by D1, and you'll also have K1. So whenever there is a dielectric, the capacitance gets multiplied by the dielectric constant, right. So C2 is K2 A epsilon naught by D2. So similarly you'll have their sum A epsilon naught by D1 plus K2 A epsilon naught by D2. So this A epsilon naught is common everywhere, so you can cancel it, not the two of them, the one you can cancel, right. So yeah, that can be done. So you have K1, K2, D1, D2, A epsilon naught. Okay, fine. And what do you have in the denominator? So K1, D2 plus K2, D1. So LCM I am taking upon D1 plus D2. Okay. So now, so this is the we have two things in the denominator, so we can flip it and take it to the numerator. So K1, K2 upon D1, D2 into A epsilon naught, and we have flip it. So what will happen? Okay, fine, we'll see what happens. D1 plus D2 upon K1 D2 plus K2 D1. Okay, something is wrong. Okay, so we'll carry on. So in series, yeah, this is the formula, right. So now we have C as, so this C will be K effective A epsilon naught by D, right. D here is D1 plus D2. Okay, so D1 plus D2. Okay, so here you are supposed to compare these two and get the answer, right. So are we doing a mistake over here? So K1 A epsilon naught by D, D2, okay, this is product, right. So that will go on top and this will cancel. Okay, so you have your K1 K2 A epsilon naught by K1 D2 K2 D1, and you can cancel in fact A epsilon naught, and you'll have K effective as basically K1 K2 to D1 plus D2. Yes, this is correct. K1 D2 plus K2 D1, which is option C. Okay, this should have been K1 D2 K2 D1. Yeah. Okay, so that's how you do this question. Just find the equivalent capacitance, equate it to this. Basically, it will be K effective A epsilon naught by the distance, right? D1 plus D2, and you can find the what will be the effective dielectric constant of this system. Okay, so over to the next question. We have question 6 and 7. In question 6, we are given the variation of potential with the distance x. Okay, so in the SI unit it is given. You are supposed to tell what is the electric field at x is equal to 30. Now x is equal to 13 is somewhere here, right? You know it, between 12 and 14. So you can see there is the slope to this graph. If you were asked for the electric field over here, it would have been 0, right? Because there is no slope, and you know that electric field is nothing but minus dV by dr. Okay, or in this case you can write it as delta V by delta R. Okay, change in voltage with respect to the distance. Okay, so here nicely you are given 2 points. One is this, one is this. So you can find the slope, right? So minus of delta V. So again the slope is going to come out negative, so since the line is facing this way, obtuse angle with the x-axis. So slope will be negative, so the final answer will be positive. So this and this you can neglect. Okay, so let's see the value. So delta V, y2 minus y1 upon x2 minus x1, right? Y2 is this one 30 minus x2 is 10 upon y2 minus y1 upon x2. Okay, x2 will be 12 and x1 is 16, right? So this will be your value. What is that? So this will give you the negative sign, cancel out with the outside one. So 30 minus 10 is 20, 20 by 4. This should be 5. Okay, so option B, 5 volts per meter. Okay, let me just check that. Yes, it is correct. Okay, so 5 volts per meter. Okay, and you could have made it out from the units as well, that you are supposed to take the slope, right? Because it is volt per meter. Okay, volt per meter. So you were supposed to take the ratio of some kind. Okay, let's come to this one. Here we have a combination of capacitors. Okay, you are supposed to tell what is the C equivalent in this case. Okay, it might seem quite complicated, but it's not. You just have to look at the voltages at this different points. Okay, where the capacitors are connected. Each one is C. So if you see this point and this point will have potential same, right? A, because there is nothing resistor or capacitor, nothing of that sort which drops your voltage. This is basically a wire, right? There is no potential drop across wire. Okay, ideal. So here also we'll have B. Here if you see again here we'll have B. Okay, so I've named all the points, and here this point we can call C, since a capacitor is coming in between. So we'll call it some other potential C. Okay, let's call it D because we have C zone. Okay, so now just take point A, B. You are supposed to find across AB. So let's put the D in between them. So if you see this capacitor is between A and B. Then we have this capacitor between D and B. Okay, so this is counted, this is counted. You see this one again between D and B, right? It's just written in a fancy way, but if you see again between D and B, right? So, and if you see this one, it is between A and B. Okay, fine. So this is the combination you are supposed to solve. Now it's easy, right? Because if you see this is CC, so you'll have C plus, so this will be 2C, right? In parallel the capacitance adds. So this 2C is in series with this one. So 2C and C in series. If you know the shortcut, it is 2C by 3, or I'll show you how it's done. So 2C and C in parallel, right? 2C, this is 2C and C in series, sorry. So in series, you have to take product upon sum. So product upon sum. Okay, so now you'll see why it is. So 2C square by 3C, right? So this is 2C by 3. So basically the bigger of the two divided by 3. Okay, so that is what I tell you. Okay, so it's a trick. So now it is 2C by 3 in one branch, and we have C in the other branch. Now they are in parallel, right? So this is effectively brought down to this. So they are in parallel, so C equivalent will be their sum, 2C by 3 plus C. Okay, So 3C plus 2C, 5C by 3, which is option D. Okay, so that's how you simply break down the circuit and do this uh, and find the C equivalent. It was that simple, just looked a bit complicated. I might have a whole video on this. I'll also link that in the description. Just a different form of this, wherein we have different plates. You might have seen those type of questions, wherein you have different plates connected, okay, and you are supposed to tell their capacitance equivalent. So I have a video on that. I'll link it in the description below, so you can practice those type of uh, capacitance questions as well, right? It was one of the important topics as we saw, and most of the questions were from grouping, right? Series parallel. So yeah, to check that video out, over to the next question. Question 8 and 9 over here. In question 8, we have a circuit. We are supposed to tell what is the energy stored in the 6 microfarad capacitor. Okay, so of course you can look at the circuit and analyze it. This will be 8, this will be 0, this will be, if this is 0, this will be 12, so 12, and this is 8 and this is 0, right? So 12 minus 8, so the voltage drop is of 4 volts, okay? So, and the capacitance is C is 6 microfarad, right? So you can find it easily, or you can use Kirchhoff's law if this is confusing. Okay, you can find Q, and you can find half Q square by 2C, right, or Q square by 2C. Okay, so that will give you the answer, or use simply Kirchhoff law. So we'll go in this loop. Okay, so beginning from this point, so minus to plus, so plus 12, right, gain in the potential. Then you come across this, so this will be plus Q, this will be minus. So again there is drop in potential, so charge by, so potential for capacitor is Q by C, right? So Q by C, C is in microfarads. Okay, so place it like that, and then we have a drop in potential, right? Higher potential to lower potential. So we are only going in this loop, so that is unrequired. Okay, so let's come to this. So we have 4, and this will be Q by 6 microfarad, right? 12 minus 8, 4, and take this to the other side. So you have Q is equal to 6 4 are 24. This is in microcoulombs, right? So potential or the energy stored will be Q square by 2C. So Q square is 24 into 24 divided by 2 into C. C is 6. 2 6 are 12 and 12 2s are, right? And this is all in micros, right? So micro, this will be micro square actually, but again we have capacitance in micro, so 1 micro will get cancelled, and you have the answer in microjoules, okay, or 10 to the power minus 6 joules. So 12 2s and 24 2s is 48, and that in microjoules, which is 48 into 10 to the power minus 6. Okay, so I think you could have done it this way also, half CV square. Okay, so half C into V square, right? So 3 4s are 12 and 12 4s are 48, right? Same answer, and in microjoules. Okay, so yeah, physics does not lie. Let's come to the next question. So here we have 8 equally charged drops, which will combine to form a bigger drop. So 8 drops which have, actually they have equal potential also. So if the potential on each small drop is 10 volts, so they have each one has a potential of 10 volts. They combine to form a big drop. Now what will be the potential of that big drop? Okay, so again it won't just add up, you'll have to think about it. So first of all, you'll see that the volume will be conserved, right? So in this case, whatever the volume of this 8 drops are, they combine to form the bigger drop, right? So the volume is conserved. So 8 times the volume of this small drop, so 8 times the volume of one small drop, which is, let's say the radius of the smaller one is small r and the capital one is capital R. Okay, you are supposed to tell the potential of the big drop. So potential of the big drop will be basically KQ by R, right? But you don't know what this Q is, you don't know what this R is. You'll have to obtain it in the form of the smaller drops. Okay, for that you know the potential. Okay, so you'll have to do some manipulation. So 4 upon 3. So for this one we have 4 by 3 pi R cube. Okay, so now you can see 4 by 3 pi cancels. So if you take cube root on both sides, so R will be 2 times of R, right? 8 is 2 to the power 3, so cube root of 8 is basically 2, right? So you know this r in terms of small r, fine. Now you'll also given that v for the smaller one, small, is kq by r, and it is 10, right? K, the charge on the smaller one, which we take as small q, and the radius of the smaller one is r. Okay, so for each drop it is 10 volts. This also we have. Okay, so we are basically finding a relation between q and this small r and capital R. Okay, now we have the relation between capital R and small r. How do we find the relation between q and q? Now the charge will directly add up, right? Conservation of charge. So 8q will be basically q. All the charge will nowhere be lost. Okay, so when you put this 8 charges together, 8 drops having equal charge q together, so 8q will form this capital Q. Okay, so charge is not lost. So now substitute this k into 8q divided by r. R is 2r. Okay, so this is 4 times. So 4 times kq by r, and you know that this is potential for the small drop, and for the small drop it is 10. So 4 times 10, which is 40. As simple as that. Okay, so you just had to find a relation between this, relate this radius of the bigger drop and the charge on the bigger drop with that of the smaller one, and that leads you to your answer. Okay, so that's about this question. Over to the final question for the day. Then your final question for the day. In question 10 we have 3 charges, q1, q2 and q3. So q3 is along the arc, it is moved along the arc, so it is initially at a distance of 40 centimeters from the q1. It stays at that distance only the thing is it is moved along the arc. Okay, so basically if you complete it, it will be a circle, but it is moved from here to here. Okay, again it remains at the distance 40 centimeter from q1. Okay, so it's moved along arc of circle radius 40 centimeters. Okay, the change in the potential energy of the system when that is done is this. Okay, you are supposed to tell the value of this k. Okay, so let us find the change in potential energy. So initial potential energy, so initially this is the configuration. So what is the initial potential energy? So you know it's k q1 q2 by r, right? So k, so you have system of charges, so q1 q2 by first one is this 30, right? So actually this is not going to change, right? Anyways it will get cancelled in the final potential energy, since only this charge is moving. Okay, this relative distance has not changed, but anyways for the correctness we'll write it. So you'll see that it gets cancelled. Okay, then we have this charges we included, then we have to include this too. So q1 q3 and the distance between them is 40, and q1 q2 you also have to include. So what is the distance? This is the distance, right, separating them. So 3 4 5 or 30 40 50. Okay, Pythagoras triplet, or you can use the Pythagoras theorem to find it. So that will give you 50. So finally what happens is q1 q2 and q3 will be in one line. Okay, so this distance is 30. Okay, no, nothing has changed over here. Then this distance will be 10, because this total distance is 40, right? Because this is 40 total, so this is 30, that will be 10. So this is 40. Okay, now what is the final potential energy? So again between q1 and q2 nothing has changed. Then we have q2 and q3 separated by a distance of 10 centimeters, and finally q3 and q1, right? So that also has not changed, q3 and q1, which is 40. Okay, so if you take the difference, so they have asked you for the difference, right, in the potential energy of the system. So this and this cancels, as I assured, and also this and this will get cancelled, right? So final minus initial, so this q2 q3 by 10 minus q1, this should have been, what is this, q2 and q3, right? So q2 q3 by 50. Okay, so q2 q3 is also common, so we have, also you can take 1 by 10 common, so 1 minus 1 by 5, so that will give you 4 by 5. So k Q2, Q3. Now this is not this K, this is 1 upon 4 pi epsilon naught, right? So 10 and you'll have 4 by 5. Okay, so again, if you see all the units are in centimeters, so you have to pay attention. You bring it into the SI unit, right? So you multiply this by 10 to the power minus 2 or take 100 in the numerator. Okay, so that also lose. So this and this will get cancelled. 5 2s are 10. And what do you have? You have your answer over here. So this is 1 upon 4 pi epsilon naught. We have Q3. What is left? 4 2s are, which is 8 Q2, and the rest is there, right? 1 upon 4 pi epsilon naught. Q2 is there. Sorry, Q3 is gone. Okay, so it's there. So this thing is gone. What is K now? K is the remaining thing. So this is Q2 into 4 times 2. So 4 2 is 8, 8 Q2, which is option A. Okay, so that was the way to do this question. I hope you know to deal with the system of charges to find their potential energy. So that's about this video. I hope you really enjoyed it and you'll join me in the grind. We'll continue this for 12th standard and we'll bring a fresh series for BITSAT 2025, and that will have the most impact for your preparation of 2025. So stay tuned for that. Firstly, we'll complete this series. So join in for the grind for every week, wherein we are getting 10 questions stronger in every BITSAT chapter. So that's the aim of the series. I hope to see you in the next one. Till then, keep enjoying physics.